This video will show you how to calculate a chi-square between two qualitative variables. Before we see what the chi-square statistic is, we will first revisit what is a qualitative variable. If you remember well, qualitative refers to categories or observations. Here are a few examples. The qualitative variables can be divided into two categories. The first one is nominal, which classifies data in mutually exclusive categories with no possible ranking or order. The second category is ordinal. These can be placed into categories and ranked, but there is no precise measurement possible. What the chi-square measures is the difference between what would happen if we were in a situation where only chance plays a role versus when there's something influencing the result. For example, if you roll a dice 1,500 times, because every value has the same probability of occurring, you would expect that your end results are anywhere close to this. So 1,500 divided by 6 is 250. It is quite possible, though, that you end up with something slightly different. For example, this. These variations would probably not be sufficient to arouse your suspicions, and you would accept these results quite gladly, because although they're not exactly the same, they are close enough to what you would theoretically expect. On the other hand, if your results look like this, you would rightfully suspect that something here is influencing the results because the results are way too far from normal variation. You could suspect that the dice is actually loaded and as such influences the results by having one come out more often than it should. Again, the chi-square measures how far away from the results you'd expect in pure probability than what your actual observed results are. When we wish to calculate a chi-square, we must first create a table of contingency. In the table, the rows represent the values of one of the variables, and the columns represent the values of the other variable. As an example, we'll do a table of contingency for the Canadian House of Commons after the federal election of 2011. Our first variable would be the political party, for which we have Conservatives, the NDP, the Liberal Party, the Bloc Québécois, and the Green Party. Our second variable could be Canadian regions, for which we could have BC, the Prairies, Ontario, Quebec, and the Maritimes, as well as the territories. Now these are the corresponding values. These tables give us a lot of information. For example, we can say that there are 3 deputies in the Prairies that have been elected under the NDP banner. We can also say that there are 50% more Conservative deputies in Ontario than in the Prairies. Another tidbit of information is that the only region that has elected a Green Party deputy is British Columbia. Although this is all interesting information, the table is currently lacking something crucial in order for it to become a contingency table, the totals. Now we must add the totals for each column in each row like so. The final cell represents the grand total of the table, which you obtain by either adding all of the row totals or all of the column totals together. Now it is a good idea to double check if both of these totals are actually equal to each other. If they are not, it means that you have made a mistaken calculation somewhere. Now this table, the contingency table that we have right now, gives us the observed values of what is currently happening in the House of Commons. Now, there are actually 308 deputies in the House of Commons. I have omitted the independents to make this a little bit simpler. We know that who is elected is certainly not due to probability only. For example, if you are running for office in Quebec, you have a better probability of being elected if you are running with the NDP or the Bloc Québécois than if you are running with the Conservatives. You also have more chance of being elected in the Prairies if you are running with the Conservatives than if you are running with the NDP. But the chi-square statistic tells us how far away our actual observed values are from what would be expected to happen if the situation was only controlled by pure probability and giving us the same totals. We must find what these expected values would be. The idea behind finding expected values is proportions, or using the rule of 3. Let's consider the first cell, conservatives in BC. How many conservatives in BC would be expected to have under pure probability? Well, what you have to do is take 165, multiply it by 36, and then divide that by 306. Your total will be 19.41. So under pure probability, you would expect to have 19.41 conservatives in BC. Logically, we know that you can only have entire deputies, but remember these are proportions in pure probability, so you should always keep the decimals when you're calculating expected values. Now maybe this would be an easier way for you to understand how to calculate expected values. An expected value is actually equal to the column sum times the row sum of the cell divided by the grand total. Let's do another example. So with all proportions kept, what would be the number of NDP deputies in Quebec? The column total is 100 multiplied by the row total of 75 divided by the grand total, giving us 24.51. Now here is the entire table of expected values if you were to obtain the same totals under pure probability. We now have everything we need to calculate the chi-square statistic for this given situation. Again, remember that the chi-square statistic tells us how far apart the observed values are from the expected values under pure probability. Here is the equation to obtain chi-square. We have first the symbol for chi-square. Then the equation states to sum all of the following results. From a given observed value, subtract the expected value. Square that result, and then divide by the expected value. Basically, you must calculate a value for each individual cell and then add them all up together. Let's do an example. Now here's the table of expected values, and I have put the observed values in parentheses. The value for the first cell would be 21 minus 19.41, all of that squared, divided by 19.41. So our value for that first cell would be 0.13. Now the value for the second cell would actually be 13.93. Remember that we are checking how different these values observed and expected are from each other. So it makes sense that you get bigger output values for original observed and expected values that are wider apart. And here is the completed table with all values for all cells. I voluntarily left in the table the very small values just to show you what they are, but remember to round to 2 decimals. Theoretically, the only time you will have a true zero is if the observed value and the expected values are exactly the same. Finally, to obtain the chi-square, you must add all the values you have just calculated. You can either add up all values at once, but you have a higher chance of making a mistake. A second method would be to add row by row as so, and then to add your results for the grand total. You can double check by adding column by column and then adding those results. If the total results are the same, then you have summed up well. We now have the chi-square value for our House of Commons, which is 159.31. In the next video, we will see how to determine if that chi-square value is actually high enough to consider that the differences between expected and observed values is significant. But before that, it's your turn to calculate a chi-square. So pause the video and calculate the chi-square according to these 3 steps for this table of observed values for snacks according to the gender of the snacker. The chi-square value for this table is 6.34.